We're going to use this problem to introduce one of the very basic concepts in highway design, which is design stopping distance or stopping sight distance, whichever you want to call. So we do that by taking two drivers, one traveling at 50 miles per hour and the other at 75 miles per hour, and both of them have the equal reaction time of 2.5 seconds, and we will change some of the variables, specifically the slope of the roadway, and one level road, one downward slope, one upward slope, and then bring the green book values in here and also introduce the equations all in one shot in this problem. So let's see what, again, one more time, the problem is reaction time for both drivers is 2.5 seconds, and vehicle 1 is traveling at 55 miles per hour, vehicle 2 is traveling at 75 miles per hour, I'm sorry, 70 miles per hour, and the grade in the first case is a negative 2.5%, meaning it is a downward slope and vehicle is going in that direction, it's going downward. So you would imagine the downward slope is adding to the stopping distance requirement. So A, acceleration or the deceleration rate, in this case deceleration rate is not given, but the AASHTO 2011 version of AASHTO recommends using of 11.2 feet per second square as the deceleration rate, and let's use that. But the reason I left deceleration rate blank is that it is something that you can substitute or you can use the design value. So the reaction distances are given by velocity times t, that is the reaction distance, using your simple rectilinear motion equations. So for vehicle 1, which is traveling at 55 miles per hour, the distance traveled during the reaction time, which is dr, is going to be velocity or the speed is 55 miles per hour, 55 mph. And remember, every time you have miles per hour, you have to, well, we are solving all these things in feet, so we will convert it to feet per second, which is the conversion factor 1.47 feet per second for each mile per hour, and the reaction time is 2.5 seconds, and the value comes out to be 202.1 feet. That is the distance traveled while driver 1 is reacting, and it took 2.5 seconds to react. For the second driver, it is going to be similar. So 70 miles per hour, converting miles per hour to feet per second is 1.47, and same reaction time of 2.5 will get you 257.3 feet. Now the other component is, of course, I just brought the values here, neatly typed for your convenience. So the second component of the stopping distance is, first is the reaction distance, and the second component is stopping distance. So the stopping distance is given by the equation velocity square, or the speed square of the speed, divided by 2g times a plus 32, a divided by 32.2 plus g. And substituting these values, of course, on the numerator you have the speed, which is, for driver 1 the speed is 55 miles per hour. Let's put this a value as 11.2 feet per second square. So let's substitute these values as usual. Speed is 55 miles per hour, and we usually convert it to feet per second. 1.47 is the conversion factor, 1.47, and then the whole thing is squared, divided by, you have 2 times acceleration due to gravity, which is 32.2 feet per second square, and the a value we have 11.2 feet per second square. 11.2 divided by 32.2 plus g here. The G value is given as minus 2.5%, or it's going to be minus 0.025. So that's what we will put here, 0.025, and the value you will get is 314.4, 314.4, which is feet. Doing the same thing for this vehicle 2, which is 70 miles per hour, doing exactly the same, except in this particular spot we are going to put 70 instead. So you will get a value of 509.3, and the value, the total design stopping distance, are also known as stopping sight distance, SSD, is going to be, for the first guy 55 miles per hour, is this guy plus, and that value, which is 202.1 plus 314.4, that equals to 516.5 feet. Similarly, design stopping distance, or SSD, for vehicle 2 traveling at 70 miles per hour is 257.3 plus 509.3 feet. So that will be 257.3 feet plus 509.3 feet. So that is 766.6 feet. Very simple computations. All you got to know is SSD is reaction distance of dr plus stopping distance of d, and this is going to be v times t, and this value is, as we mentioned here, that is the second guy, v squared divided by 2g, etc., etc. Now, so did the same computations for 3% upgrade. The distance traveled during the reaction time is not going to change. Well, theoretically speaking, it does change, but for all practical purposes, it is considered unchanged, the reaction distance. But the stopping distance, of course, is going to be a good function of g, because you see that in the denominator, g value. So that changes, and the new computations are going to be like this. And what we have, the design stopping distance at a slope of plus 3%. So plus 3%, you would expect this design distance to be a little less than the one in the downward slope. If 3% is going up, minus 2.5%, which we did earlier, is going down, so this guy will have higher stopping distance. So we had earlier 516.5 feet for minus 2.5% grade, 2.5% grade. Same thing for 70 miles per hour, you have 766.6 feet. So this is how you will get the picture, what happens when the grade is positive versus when the grade is negative. Downward slope requires higher stopping sight distance. Now let's do the flat one. Exactly the same phenomenon. It will, as you would guess, it will be somewhere in between, which is the case. We have the stopping sight distance for 55 miles per hour as 493.9, and for 70 miles per hour it's 729.9. So the grade here in this case is 0%, or it's a flat surface. Now the problem asks you to compare them for Green Book values. So I just put the Green Book table in here for comparison purposes. So what we got for flat, which is 0% grade, 0% grade, which is G equals 0%, we have the reaction distance are 202.1 and actual stopping distance of 292.8, stopping side distance as 493.9. Let's compare them in the table. So the design speed is 55 miles per hour, and let's draw a line here and then compare them here. So brake reaction distance. So this is the reaction distance dr, which is 202.1, which is 202.1. What we also got the same thing, and we computed this part to be something like 292.8. So we are slightly higher because they used some extra rounding while using the design parameters. We will see what that is just a bit. And what we have total computed stopping side distance of 493.9, and they got 492.4, and the actual design value that is recommended is 495, which is slightly it's to the next 5 feet increment, which is next 5 feet increment here is 495. So that is what is recommended here. Same thing you can see for 70 miles per hour vehicle, and it's going to be, this part is same, the second part is we got slightly higher value, 470.3 versus 472.7, and the third one, the total stopping side distance 729.9, the green book has 727.6, and the design value is to the next 5 feet increment, which is 730 feet. So this is how the green book values are given to you. You can use the formulas in one shot. This formula is basically the design values here, the way highlighted in red. What we computed is 493 point, say in this case 55 miles per hour, and we got the green book shows you 495. All these things can be computed in one shot with one equation. And if you look at some of your textbooks would have given this formula. If you have an older textbook, you will have a different formula. That's not because they are wrong, that's because older versions of AASHTO Green Book has different formula for stopping side distance. But this is AASHTO Green Book 2011 version. Depends on when you are watching this video. 10 years from now, that may not, these values may not be valid. Anyway, now this is the generic formula. Generic, of course, US customary units. And if you want to use very specifically V in miles per hour, remember we constantly keep on using that conversion factor of 1.47. So this is, if you want to use directly V in miles per hour, you will use this formula, whereas here V can be either in feet per second or wait a minute, yeah, it has to be in feet per second. You have to convert it into feet per second. Directly here you have to substitute V value in miles per hour. The conversion is taken care of in the denominator, this 30 as opposed to 2a, you have 30. So this is the formula you will see in FE reference book. And depending on which textbook you are using, you may see this formula or this formula. So whichever it is, as long as you understand you are applying the formula correctly, you shouldn't have any problem. If you are reviewing this for FE exam or for PE exam, you can expect 1 or 2 questions in this very easily. So thanks for watching.